So in the previous lesson, we were discussing a block on a horizontal plane, and what we basically said is that we have forces acting on that, namely the force of gravity pulling it directly into the table. We have the force of the table, or the normal force, opposing gravity, and then we would pull on this block with some force to get it to move. And if we were right at the point of sliding, we could say that the force of friction would equal the pulling force at that time, and we could calculate the coefficient of friction based on this force of friction and this normal force. Now, what we're going to do, instead of using a LabQuest to pull the block, we're now going to utilize gravity by raising the board that it's sitting on, and therefore having gravity pull it down the incline a little bit. So in order to solve these problems, we have to again look at the free body diagram. If this is our block and this is our board that we have lifted to some angle that we'll call this angle theta, we can say that gravity obviously still acts, and gravity acts straight down. So now, when you look at this, if we were to rotate this plane, we can see that gravity is not pushing all of its force into the board. Rather, only a component of it is into the board. Which makes sense if you think about it, because if we were to split this vector into what are called components, which are like your side A and side B of a triangle, and we were to make, in fact, a right angle, so that we have a right triangle, we could say that we have two components that make up this force of gravity vector. This would be your force of gravity in the y, and this one would be your force of gravity in the x, and it's this little vector right here. Drew it down so that you could read it. So what we're now going to do is we're saying as we lift this board, some portion of the gravity is pulling this block down the ramp. This is increasing as the amount of force into the board is decreasing, because as you know, as you lift that board more and more, the force on the board gets less and less. If you were to take the extreme case and you were to just stand it straight up like so, and you still had your block, now the entire force of gravity is pulling it down the ramp, if we call that a ramp, and there is no component that's going into the board. So your normal force here is going to be 0 because there's no push on the board, so there's no push back. There's no action-reaction pair there. So let's go back to this example here. Okay, so we want to figure out what force, because what we're doing is we're lifting this until this block begins to slide down the ramp. So we want to figure out how big does this force of gravity, this x component, have to be in order to overcome the friction that's holding it back. If we can figure out this, that's going to tell us the maximum amount of friction between this block and the table, which is what we're shooting for. Also, we'll be able to get the normal force, because the normal force, whereas before we could just say it was equal to gravity, the normal force is the surface pushing back on it. So it's not going to be equal to gravity anymore. It's going to be equal to just this component. So we're going to have to use our trig functions in order to solve for the normal force and the force of gravity. So how do we do that? If we think back to our triangles, we can say, okay, so the force of gravity in the y. Let's start with this. Okay, I'm going to do it right over here. I guess I better jump back to, since this block is on this angle, we can say that this angle right here is also theta. So now we've got an angle. We know our force of gravity because we can calculate that, m times g, and we can solve for this component knowing the angle and the force of gravity, which is really our hypotenuse. So now, for the force of gravity in the y, which will be this component right here, the component that's pushing into the board, since we're looking for the adjacent to the angle, we have the angle and the hypotenuse, we're going to use c, right? And c is cosine theta is adjacent over hypotenuse. And now we can go and we can plug our numbers in. Cosine theta, whatever theta is, times the hypotenuse is going to give us the adjacent. If I were to now use the symbols that I'm using up here, I'm going to say FGY is equal to the force of gravity times the cosine of theta. You can plug in your numbers for your angle and for your weight, and you can solve for this component. This component will be equal to your normal force. Sorry about that. And now if we wanted to solve for it in the x, we'll go below and solve for it down here. And so if we're now solving, for the x one, which corresponds to the force of the component of gravity that's pulling it down the ramp, which therein is going to tell us the force of friction holding it up. This is the one that we're continually increasing. Again, I'll repeat that because that's the important part. We're making this one bigger and bigger by lifting it more and more. As this angle grows, the force of gravity pulling it down the board grows until you get to this spot right here when all of it is pushing down. So to do this one, since this is the opposite of the angle, we're going to use SO, which is sine theta is opposite over hypotenuse. We rearrange this. Hypotenuse times the sine theta equals opposite. Plugging in our variables, FGX is going to be equal to the force of gravity times sine theta. All of this, so FGX is going to be equal to the force of gravity, the component of gravity that's pulling it down the ramp, which is equal and opposite to the force of friction at its point of sliding. Now we've got point of friction, or force of friction, we've got normal force, and we can solve for the mu being force of friction divided by the normal force. And so that's how we can utilize gravity to calculate the coefficient of friction on a ramp or in 2 dimensions. That's all.